Okay, so it says in the figure at the right, a particle of mass 0.67 kilograms is a distance d equals 23 centimeters. So you've got this. So here's M1, and you're told that it is 0.67 kilograms. And then you've got this rod here, which I'm going to draw small so that we have room. You're told that this distance here is d, which specifically is 0.23 meters. You're told that the whole rod has length L, which is it 3 meters or 5 meters?
I feel like it's
3 meters. And you're told that the mass of the whole bar is 5 kilograms. Okay? So, and what we want to do is we want to find the force of gravitational attraction between the two objects. Okay? So, if this was simply a point particle, we'd be good. We'd just do g times m1 times m2 over r squared, right? But the problem is, it's not a point particle. And specifically because for point particles, this r is squared, you can't just find the center of mass. Okay? Because these particles are going to sort of create more gravity than these ones do. Particles twice as far away are only going to produce 1/4 as much gravity. So just going center of mass doesn't work. Does that make sense?
Could you find the point on there specifically and then do it from there? Like, I don't know what point that would be.
So there's a way to work backwards, but you'd have to do the integral we're about to do and then figure out where, you know what I mean?
Yeah, okay.
So after I'm done solving the problem, I'll do that. And the last step is only one step. All right, so is everybody good up here? All right, so what we want to do is we want to imagine this thing as a whole bunch of teeny little particles of mass dm. And then sum all of them up. Does that make sense? All right, so when you do it that way, our force of gravity becomes the integral of g times m1 dm over r squared. Follow? All right, so now we're going to use that same calculus trick that you had to use when we did finding center of mass, when we did finding rotational inertia, and when we did drag force. All right? They're all the same trick. It's substitution. Okay? What we need to do is we need to find a way to either rewrite this all in terms of m, which is ugly, or better yet, make this so instead of being dm, let's see if we can write it as dr. Okay? So one of the things we talked about when we did center of mass was we talked about linear density. And we said that linear density was the total mass of the object over the length of the object, right? And so for us, that's 5 kilograms over 3 meters, right? Good? Now the operative word in all of these problems, it tells you that it is a uniform rod. Which means that the density of any little chunk is the same. So this is also equal to the mass of that little chunk there divided by the length of that little chunk there. Follow? So, am I going too quick? Are we good? So, if we multiply both sides by dr, we find that dm is 5/3 of dr. And so now, this integral becomes the integral of g times m1 times 5/3 dr all over r squared. But I need to set my bounds of integration. So, I'll wait till everybody's done writing that, and then I'll jump back.
It's just the length of the rod.
Not exactly. It's not exactly the length of the rod because how close is the closest particle?
D.
D. So we want to go from 0.23 to 3.23. Does that make sense?
Yes.
Right? Because that's the range of radii that I need to accomplish getting all of my 5 kilograms worth of mass. So this goes from 0.23 to 3.23. Cool? So you can pull out all of the constants, so you get 5g m1 over 3 times the integral from 0.23 to 3.23 of, it's 1 over r squared. I'm going to write it as r to the negative 2 dr. Does that make sense, you guys? And so that gives you 5g m1 over 3 times, what, negative r to the negative 1? Right? Wouldn't that give you r to the negative 2 if you differentiate it? And then evaluate it between 0.23 and 3.23. And then solve it. Make sense, you guys, or no? All right, this trick here, you guys, is very common. All right, we've now seen 3 places where that comes up. Center of mass, rotational inertia, and now gravity. Okay?
So what if the fall was not on the same axis?
Then it gets crazy complicated and you need more calculus than you probably know. Good? I didn't mean that to sound snarky, but I don't know if I would know it, to be honest. I would need to. All right, cool, you guys?